Okay. Now, as their name suggests, the memory reference instructions generally are used when we need to fetch an operand from the memory. Okay, so when the operand on which a particular operation is to be performed is residing in the main memory, then the instruction that I use is called as the memory reference instruction. Let us have a look at some of these memory reference instructions. So this is a table which has been taken from your book, M. Morris Mano. Okay, and the first column here describes the symbol that is used for the instruction, for the memory reference instruction. And here in the last column, you can find the description. I'll be talking more about the second and the third columns, which happen to be the corresponding opcodes. That means the operation codes for this particular instruction, let's say, and the operation code, how this operation code will be specified in binary. So in binary, what will be its operation code, that I will discuss sometime later. Okay. The first memory reference instruction is AND. Okay. Now, what does it tell me to do? It tells me that you please AND the memory word to AC. Okay. So suppose I write down something like this. Okay. This means what? This means that go to the address 200 and whatever is written there is my operand. Okay. Please get that and AND it with the contents of the accumulator. Okay. So this is something which you have seen. I've already shown you, if you remember. Here. So you've already seen these two instructions, if you remember, add and add A and add B on the same formats. Yes or no, students?
Yes, ma'am.
So the only thing that we are now changing is that earlier we had discussed about adding. So when we had discussed about adding, I had pictorially shown to you how this operation will take place. This actually means going to this address A. Yes, the underlying address of A, of this variable A, which let's say happens to be 200 in our case now. And whatever operand is there, add it to AC, if you remember. Yes or no?
Yes, ma'am.
Yes,
Yes,
ma'am.
ma'am.
Yes, ma'am.
Yes, ma'am.
And now what we are saying, instead of add, we are simply saying and. Instead of add, we are simply saying and. And we are giving the, instead of the variable name, we are just giving the address. Why? Because we had decided that in our instruction format, we are going to use addresses. And now, I told you that in the high-level languages such as C and C++, etc., Java, you have the flexibility to have alphabetic names for addresses. These alphabetic names, or they are sometimes known as mnemonics, these mnemonics are actually your variable names. Okay, but in low-level languages, we have to deal directly with what? We have to deal directly with the addresses. Do you remember?
Yes,
Yes,
yes, ma'am.
Right. So the first memory reference instruction is and. What it it does is, we have done the logical AND operation,
Yes, ma'am.
Yes, ma'am.
Yes,
right?
ma'am.
So what this will do is it will AND the contents which are there at location, let's say 200, with the contents of the register AC. Is this clear? And the result will again be stored where? It will be stored in AC. Is this clear?
Yes,
Yes,
ma'am.
ma'am.
Yes, ma'am.
Right. Next is add. So add you have already seen. So if I say add 200, that means go to the address 200, pick up the binary operand from there and add it to AC. The result again goes to AC, and this time please see there might also be a carry out, because when we add two numbers there might be a carry out, end carry. You remember?
Yes,
Yes,
ma'am.
ma'am.
Yes, ma'am. Yes, ma'am.
That will be stored in which flip flop?
E flip flop.
E flip.
E.
That will be
Extended
stored
flip
Extended
in
bell.
flop.
the extended flip flop E. Okay, so I'll come to these, the execution of these memory reference instructions later again. I'm just trying to give you an idea of how the memory reference instructions look like. Okay, the next is LDA. Okay, the next instruction is LDA, and let's say it is LDA 200. Okay, so what it means is load into AC. Okay, load into AC whatever is placed at 200. So suppose, okay, let me just draw it here if that makes it clearer to you. So when I say, so initially please see AC might be containing anything. Okay, AC might be containing any binary number. Okay, but when I say LDA 200, what happens is that we go to the main memory at the address 200, and whatever are the contents there, and that means whatever is the operand there, we get that, and that is loaded into the AC. Is this clear? Is this clear now?
Ma'am, excuse me.
Yes.
Ma'am, then it is removed from the particular address.
No. No.
Okay. It just copied, na?
Yes.
Okay, ma'am. Okay.
Okay, so is this clear up to now?
Yes,
Yes,
ma'am.
ma'am.
Yes, ma'am.
Now, so the next instruction is STA. Okay, what that will do, let us see. So suppose my AC contained this, okay, and obviously there is some content at location 200 already, right? STA 200 means store AC at address 200. So whatever are the contents of AC, go copy that and store that at 200. Okay, so this is what happens. Is this clear?
Yes, ma'am.
Yes, ma'am.
Right? So you remember I had discussed STA here with you as well. Yes or no?
Yes, ma'am.
Right. Okay. Now the next instruction is bun. Now what does bun do? Bun says branch unconditionally to whatever address is given after it. Okay. That means uh, let us say we are executing a particular program. Wherever we are, leave that program, leave that instruction sequence as it is, and go to address 200 and start executing the instructions from there. Okay, more about bun and BSA later. Okay, more about bun, BSA, and even increment and skip later. Okay, so I'll be taking these in a lot of detail later. So I'm just giving you an idea right now. Okay, you may not understand the complete instruction at this point of time, but later you will. Okay. Next is BSA. BSA means branch and save return address. So this is again the same as in bun. What we are trying to do here is we are trying to alter our program sequence. For example, you have a if statement in your C++ program class. What happens then whenever you have a if statement? If this particular condition is true, then you can write go to this particular label, right? So you can jump certain statements there, okay, and go to a different statement. Another example is that if we encounter a function name somewhere, okay, you will be doing functions. I don't know if you started with that as yet or not. So what are functions in C++? They are additional code units. So let's say you are executing a particular program and in between you encounter a function name. So what do you have to do? You have to branch from that position. Okay, you have to branch from that position to the function's position. Okay, execute all the code of the function and then come back. That is an example of BSA. Go to statement in C++ is an example of bun. Okay, when we have you done go to statement in C++?
No, ma'am.
Ma'am, in
Not
class
yet.
12. No, ma'am. Class
Functions?
12 we are done.
No, ma'am.
Okay,
Ma'am, in 12th we have
no
done.
problem, no
In
problem. So
12th we have done.
you can just bookmark these terms as of now. In some time, after some classes, you will be doing these concepts in C++. So then you will be able to relate much better. Bun means that we simply stop executing the instructions that we are executing, okay, and we go to a different location and start executing the instructions from that address onwards. BSA means the same thing, except that after we start executing the instructions from the branch to address, that means where we have taken the branch and gone and started executing the instructions. After we have finished the instructions there, then we come back to our original instruction from where we took a branch and we start executing the instructions again. Okay. Next is increment and skip if 0. Increment and skip if 0 is if the contents of AC are 0, this instruction says that please check if the contents of AC are 0, then increment the next instruction. Okay, then increment the next instruction means increment the program counter. So I'll be talking about this to you again in a while, as I told you in more detail. Skip the basic purpose here is to skip the next instruction if the value of accumulator is 0. Now, when is the value of accumulator 0? In certain tests, we perform certain tests that if this is positive, if this is negative, if this is a overflow condition, uh, then AC is set to 0 sometimes. Okay, so in those conditions, we want to generally either perform a particular statement or not perform a particular statement. If we don't want to perform a particular statement, we want to skip a particular statement, we use ISZ. Okay, increment the PC. What do we mean by incrementing the PC? You remember I told you PC contains the address of the next instruction to be executed. Okay, so when I increment the PC, I actually am skipping the next instruction which was to be executed. Yes or no?
Yes, ma'am.
Yes, ma'am.
Okay, so this is the meaning of increment and skip if 0. But even if you've not understood this completely, the last 3 instructions, we will come to uh, them again in much more detail. Okay. Okay. Now, the memory reference instructions themselves, please see, are of 2 types: direct memory reference instructions and indirect memory reference instruction. What do we mean by these? Let's see. So in direct, in the first, that is the direct memory reference instructions, if this is my instruction, okay, now the instruction itself is located in address, it is located at address 22 in the
22.
memory. Okay, what does the address, what does the instruction say? So it says add, this is the mode bit, I'll be talking about it in a minute. The instruction says add 457. What is this 457? It is the address. Okay, so we go to address 457 and what I find there is operand. So this is the kind of address instruction that I've just told you about.
Yes, ma'am.
Yes or no?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
So we go to this address 457 and whatever operand is there, please see we add this to AC. We add this operand to AC and the result is again stored back into AC. Okay. This is a diagrammatic representation of the same thing that I have explained to you. Any problems up till now?
No, ma'am.
No,
Very good.
ma'am.
Now, what is an indirect? This kind of an instruction is known as a direct instruction. Okay. What is an indirect instruction? In the indirect instruction, the address that I get here, it is the same except for the mode bit, which I am going to be talking about in a minute. But in the address part, the address that I get is not where the actual operand is residing. Okay. Instead, the address that I get, when I go there, I get another address. Okay, I get another address at which the operand is actually located. Okay. So in the direct instruction, the operand was located at the address given in the instruction itself. But in the indirect instruction, the address is not located in the address given by the instruction. Okay. How do we find the operand then? We first go to the address which is given by the instruction. There we find another address. At which position, at which location in the memory the actual operand is residing. Okay, this is the only difference between the direct and the indirect instructions. So, since there is an additional indirection, okay, so you see, instead of going directly to this address and finding the operand, we are going to this address, and then, you know, we are getting the actual address of the operand. The actual address of the operand is also known as the effective address. It is known as the effective address. In first case, the effective address is what? The effective address is
457.
457. Very good. And in the second case, the effective address is
1350.
1350. Yes.
Excuse me, ma'am.
Yes. Yes. Tell me.
Of the instruction, the memory reference instruction.
Can you come again?
Ma'am, the 22 that was in the first diagram, that is the address of the instruction in the memory.
Yes.
Okay.
Yes, we are not talking about this address. We are not concerned about this address because this is where the instruction itself has been placed. So immaterial of this address 22 or the 35 address in the second case, we are not talking about these addresses. We are only talking about the address part of the instruction. The address that is given to me by the address part of the instruction. Okay. So depending upon if in the first case, if the address given to me by the instruction is the effective address. Okay. What is the effective address? We just said effective address is the address where the operand is found. Okay. If this address is the effective address, then this instruction is a direct memory reference instruction. And if the instruction gives me the address where the effective address will be found, then it is a indirect memory reference instruction. Any problems up till now?
No, ma'am.
This difference is clear?
Yes, ma'am.
Why do we need to have these two types of instructions and all this I will be talking about later. Okay, we have a complete section on the addressing modes later, so there I will discuss. Okay, right now the idea is just to explain to you the idea of this mode bit, and that is why I'm explaining the two types of instructions, that is the direct and the indirect instructions. Okay, so please see, in both the cases we have an address here. Yes or no?
Yes, ma'am.
How to know that this address is a direct address, effective address, or the address of the effective address? How to know?
Ma'am, by mode.
Ma'am, using
That
mode.
is, yes, that is what we can distinguish using this extra bit that we call as the mode bit. So if the memory reference instruction is a direct memory reference instruction, then I set the mode bit to 0. In other words, if the first bit of the instruction, that is the highest order bit, is if this is 0, then I get to know that this at this address, whatever is written, because you see, even this will be in binary and even this will be in binary, right? Both these contents are going to be in binary only, right? So how to distinguish whether it is an operand or an address? By this bit we know. Okay, so if the highest order bit is 0, that is the mode bit is 0, it implies that this is a direct instruction. And in that case, I only have to perform a single memory access. That means I only have to go to one particular location, and whatever is uh, stored there is going to be my operand. I have to perform my operation with that particular operand. In the second case, however, if the mode bit is 1, it means it is a indirect memory address. In that case, this address should not be treated as the effective address. This should be treated as the address of the effective address. Okay, so I will have to perform how many memory access now? 2. First to this location 300 where I will get the effective address. Second to the location 1350 where I will get my operand. Is this clear?
Yes, ma'am.
Yes, ma'am.
So now you understand why this is one of the reasons why we had put this mode bit. Okay, I had told you that I'll explain this mode bit later. Okay, so this is why we use this mode bit. This is one of the reasons. There is another reason, I'll come to it later. Is this clear for the time being? It is used
Yes,
to
ma'am.
distinguish between a direct and a indirect memory address instruction. Okay. Have you done pointers in C++?
Ma'am,
Not yet, ma'am.
Not yet. Okay. So some of you have a computer science background. They might identify with this concept of the indirect instruction, where this is used, where
Yes,
this is
ma'am.
used. So
Yes, ma'am.
what is this actually? This is address of a address. Yes or no?
Yes, ma'am.
Isn't this something like pointers?
Yes, ma'am.
Yes, ma'am.
Okay. Now, people who don't have a computer science background don't need to panic. This is not something that you are going to miss out on if you don't understand the concept right now. So again, as I said, you can just note this term somewhere with you, okay, and put a bookmark on it. And in C++, you are going to talk about pointers. So then you can relate to this concept. Okay. But for the time being, is the difference between the direct and the indirect instructions clear to you?
Yes, ma'am.
Anybody to whom this is not clear?
Excuse me, ma'am.
Yes.
Ma'am, can we get address at effective address at third or fourth step?
See, in the normal, in the computers nowadays, you may have an address of a pointer again. So that will add another level of indirection. In that case, you can get, but for your syllabus or the basic computer that we are concerned with, this book, this is outside the scope. I mean, we are not going to the third or fourth level of indirections. Though that is theoretically possible. Theoretically, it is possible. But we may have to see the practical usage of such a concept. Okay?
Yes, ma'am.
So if you are asking me this question vis-a-vis your syllabus, no, we are not going to do it. Okay?
Ma'am, is it's not practically possible?
It is practically possible. There is no problem. We can, increase the number of mode bits. If I dedicate 2 bits to the mode bit, I can distinguish up to 4 levels of indirection: 0, 0 for 1, 0, 1 for 1, 1, 0 for 1, and 1, 1 for 1. That is not a problem. Okay. But what I'm saying is, will it be actually usable? That is
Okay, ma'am.
what I'm debating. Okay.
Yes, ma'am.
Okay. Good. Now the other type of instructions are register reference and input output instructions. In the register reference instruction, again as the name specifies, these instructions only refer to a particular register. Okay, they only work with the registers. They don't need any memory access. Okay, they only work at the level of the registers. Okay, and the input output instructions only work with the IO devices. They don't work with the memory again. Obviously, these instructions need to work with the registers, but they don't need to work with the main memory. And their primary purpose is for, their primary goal is to help in the input and output of data. Okay, so let us have a look at the register reference instructions and how they look like, so that you are more clear about what we are talking about. So please see the first register reference instruction here is, this is again a table that I have taken from your book. Okay, you will find all these figures there. Now, the register reference instruction, the first one is CLA. CLA stands for clear AC. So we simply write CLA and we don't need to write anything else. Okay. Automatically what it implies is, whatever are the contents of AC, just clear all that, and that means reset AC to zeros. Okay.
Yes, ma'am.
Is this clear?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Similarly, the second instruction is CLE. CLE stands for clear E. That is the extended bit. Okay, so what it simply does is, it simply
Set the extended bit.
resets the extended bit to 0. Okay.
That means, ma'am, and carry to 0.
Yes.
Okay.
Next is complement AC. Now, what is complement? So this is something that we are going to be talking about in some classes in a theory lecture. Since I told you that, I'm taking this chapter much in advance than it should have been dealt with. So we are missing some concepts here. This will come in chapter number 3. Complements will come in chapter number 3. So I'll take it there. Okay. But the idea is, this is an operation which is again to be performed on the accumulator, and complement E means this is an operation which is to be performed on the extended bit E. Okay. Next is circulate write. Circulate write. Which register to circulate write? The first thing is AC. Okay, if it is not specified, then it will be AC. I told you, right? And E is attached to AC. It is treated as one extra bit of AC only, right? So whatever are the contents of the accumulator, just shift them to one position right. Okay. How this is done? What happens when this is done? What are the contents before and after? This we will see again in more detail. Okay. The next is circulate left. So circulate, just push the contents of AC one bit to left. AC as well as E. Okay. Next is increment. So increment is again increment the accumulator. Okay, we don't need to give anything else. So you see all these instructions, we don't require any memory access. Okay. Next is SPA. Skip the next instruction if AC is positive. So it checks to see if AC is positive. How do we get to know whether AC is positive? That means the contents of AC are positive or negative. The highest order bit, that is if AC is 16 bits long, then the 15th bit, because we start from 0. Okay, we start the indexing from 0, we go up till 15. So the 15th, if the 15th bit is 0, then it is taken to be positive. If the 15th bit is 1, it is taken to be negative. Okay, any register, right? So if AC is positive, then skip the next instruction. Skip if negative AC. If the highest order bit in AC is 1, then skip the next instruction. That means do what? PC is equal to PC plus 1. Skip the next instruction means increment PC. Is this clear or not?
Yes, ma'am, it's clear.
Yes, ma'am.
Next is SZA. Skip if AC is equal to 0. Okay. Next is SZE. Skip the next instruction if extended bit is 0. And the final one is halt. This is to stop the program execution. Okay, this instruction is used to stop the program execution. So you will be looking at all these instructions in a lot of detail, down to the very basic operations, and you will also be performing these operations in the practical classes in the CPU simulator. Okay, so please don't get worried if you think that you are not able to get an in-depth understanding of these instructions as of now. The idea is only to present you a broad concept of what do we mean by a register reference instruction. So the idea is at this point in time to concern ourselves to understand that all these instructions don't require a memory operand. Okay, clear?
Ma'am, excuse me.
Can you please take your name, please?
Ma'am, my name is Garima.
Yes, tell me, Garima.
Ma'am, can you just explain complement SE and complement E once again?
So I have not explained them.
Ma'am, just a short view.
I have not explained them. I will explain them to you in detail. Just wait for it. I've just named them for you.
Okay, ma'am. Okay, thank you.
You don't need it right now. Okay, you don't need it. The moment you need it, I will do it for you. Okay.
Okay, ma'am. Yes,
As I
thank
do
you.
with all the concepts. Don't I explain to you all the concepts that are required for understanding? Do I explain to you all the concepts that are required for understanding or not?
Yes, ma'am. You have
Ma'am,
explained.
you explained it.
Thank you. So, I'm also telling you the level at which you need to understand these instructions at this juncture in our course. We don't require this. Okay, so I don't want to confuse anybody or, take too much time here because it will unnecessarily shift the focus of discussion. Clear? I want you to stay focused on what I want to, on the point that I am discussing today. Okay, that is why I am not steering myself left or right. Now, next we come to the final instructions, the input output instructions. Just let us have a look at how they look like, what are their names. So the first one is input. Okay, what it does is it inputs a character to AC. That means accepts a character from the, as we had discussed earlier, it will accept a character from the input device and put it into the accumulator.
Yes.
Output, this instruction instructs us to take a character from AC and display it onto a output device. Okay. Then the next instructions that you're going to see again require a lot of detailed going into concept and explanations. I'm just going to name them for you, and we are going to discuss them in a lot of detail later. Okay, so as of now, you can just remember their names if you feel like. So the next instructions are SKI and SKO, skip on input flag, skip on output flag. That means skip the next instruction if the input flag is on. Next is skip the next instruction if the output flag is on. ION, IOF, interrupt on, interrupt off. Okay, so set the interrupt to on, set the interrupt to off. So please see, if I were to explain, even go into a little detail into ION and IOF, for example, it would take one entire class to explain to you first what is the concept behind the interrupts. What is an interrupt? Without explaining that, I cannot explain to you anything about it. Okay, so just let this be. This is just a glance, overall glance I want to give you of these instructions. Okay. So I'll stop here today. Tomorrow we are going to, in the next lab class, that is, we are going to take this discussion a little further and see what should be we were going to see how these instructions, how we can fit all these types of instructions in this basic instruction format. Will we need to tweak this instruction format or draw out different meanings from the same instruction format, so that using the same instruction format, we are able to specify all these three types of instructions? Okay. So that will be the discussion next time. Today, we have just learned what are the different types of instructions, and we have broadly seen we have just named some of these instructions: the memory reference, the register reference, and the input output instructions. Another very important thing that we've seen today is how to distinguish between a direct and a indirect memory reference instruction. Is this okay? This is what I want you to do today. Okay?
Yes, ma'am.
Is it clear, students?
Yes, ma'am.
Yes, ma'am.